This is lecture number 16. In this lecture, we will be talking about how the key value pairs are being managed. Key value pairs are going to be managed when the nodes exit abruptly or they go in a graceful fashion. In this scenario, how do we handle the key value pairs? They are not lost. So ideally speaking, the key value pairs should always be there in the network, irrespective if the nodes are joining in or they are leaving abruptly or they are doing it very frequently or they are doing it after a long time. So it should be the key value pair, their existence should be guaranteed in the network. So we are essentially how this is going to be maintained is what we are going to look for in this particular lecture. So there are two possibilities. Now this key value pair, how actually they are being done. So any key which we have, the way it is being stored is we compute the hash value of this. So this is a hash function. As a consequence, I will get a hash ID. And what we do is we try to find out with whatever mechanism, the way we define the root node, a root node for this hash ID in DST network. So we find out somebody who is going to be the root for this hash ID. And this node is going to be responsible for holding on to key and corresponding value pair. So it will be maintaining a database. And in this database, it is going to hold key value. So whenever somebody want to search for this key, he will just again compute the hash of this key, get the hash ID, and send a query message to this, the root of the hash ID, requesting for the key value pair. Now there are two possible ways in which the root node can actually exit the system. One is there is an abruptly, they essentially goes off out of the network. So they either are turned off or they are disconnected, either of they. So they are abruptly out of network. That's the way I should actually now term it. And second possibility is they actually gracefully exit. They are planning to shut down, so they do a graceful exit. So in case of graceful exit, I think things are simpler. So what they can do is any node which is going to shut down, he will simply collect all his key value pairs which he is storing. He will then identify a few neighbors. So if the neighbors will be say n1, n2, n3 and so on, nk. And he will now essentially divide all key value pairs into k parts. So it will create packages. Each one is going to be packaged separately. And he will send a publish message. But then now in the publish message, normally in previous lectures, the way it has been done, publish was the message which has to be sent. It has to go to the root of hash ID. So this would have been the destination thing. Then there is a key. Then we had sent a value. So, and then of course the hash, signed hash, we also call it digital signatures. So let me write a digital signatures that what we have been doing. So nobody can tamper the value. So digital signatures will consist of this particular part. So this is actually what is going to be stored in even in the database. So here not only key but the hash is also being stored. So that keeps the life simple. You don't have to compute it again. It is possible you can live without it and compute it dynamically based on requirement. It's a choice. So it may be there, may not be there. It does not matter. So even if it is not there actually stored, you can always compute the hash of the key, put it here, and then put the value and then compute the digital signature on top of it. But for verifying the digital signatures, you require a certificate of the person who has created. So his public key will be available here. With his private key only these digital signatures would have been created. And with the public key I can verify this is correctly done. So which means nothing has been tampered in these three triplets. Okay. The only thing which we need to do is now we need to insert a delay. So once the delay is inserted, this actually means this node who is doing a graceful exit has communicated the various republish pack messages to various nodes. Okay, and these nodes now have to wait for this delay. By this time, this node will be doing graceful exit. He will simply disconnect from the network. So as a consequence, and he will also tell all his neighbors or all routing table entries that he is gracefully exiting. So please purge my entry. As they are purging their entry, they will also further communicate to all the nodes. So there is going to be, like in any node, whenever a routing table entry changes, he is supposed to inform to all the entries which it contains. So that essentially there is a triggered update which happens, and this entry of this node will be moved out from everybody. Okay, so nobody will be maintaining the node ID of the gracefully exiting node. And by this actually will happen within a certain time. And we ensured this delay ensures that routing table will not have the entry for the node which is exiting. And after that, they will all do republishing of all the key value pairs which have been dispatched to them. And once they will republish, it will go to the new root nodes. Okay, and they have found out their new root nodes. Anybody want to search the same key? Again, he will take the key and then compute the hash, find out the hash ID, send the message of query, basically making a query in that, a query message. The query message will contain the hash ID and key. That's only two things it will contain. And this will go and terminate at the root node, which will then look into its own database, which is now available because of the redistribution. And the whole message, hash ID, key, value, and digital signatures and certificate will be sent back to the person who has made the query. Of course, this certificate is going to be repeated large number of times, as the large number of key value pairs will be there. We have to figure out a way to even sort this out. So we will find out a way later where we will be just replacing it by a user ID, and certificate can be found again from the DHT network. So we will essentially add another kind of key value pair into the system. We'll come to that later. Okay. So once this is done, so we can actually find out, we are able to now restore all the key value pairs in case of a graceful exit. But what happens if there is an abrupt exit which is going to happen? So abrupt exit has to be handled somehow. So let's see how this will be done. So if there is an abrupt exit, the key value is lost because node is no more there. So all key values which it was holding, they are inaccessible. They are not available to anyone. So once they are lost, how you can even republish them? You can't. So you have to do something. So it actually means that somebody else other than this root node, somebody else should also have same key value pairs with them. Same key value pairs are there at some alternate node. They will not be a root node. When this root node abruptly ends off, they need to monitor it. If it is not there, they will just republish these entries, and these entries will again end up with the correct root node and will then be used in the network. That could be one possibility. Okay. Other possibilities, we can think of the possibility of having more than one root nodes. Now, one actually will think how that is even feasible. I have only one key and I am computing hash of it. I have only one hash ID, and with this hash ID I will always get the same root node. How there will be possibility of having multiple root nodes? Now that actually is feasible if in the key I can actually append something. So I can take key, whatever is a string, I can append something. So for example, I can attend copy 1, and I can attend copy 2. So these are separate strings. Once with the same key, and I compute the hash of this, I will get two different hashes. I will get hash ID 1, I will get hash ID 2. So these will now go to a different root node. I can call it root 1, and this will go to a different root node. I can call it a root 2, and I can actually publish the entry for the same key value at both of these places. Okay. So now when a node need to search for a key either for publishing or even for research. So in this case, I am assuming it to be for research. So what he will do is he has to essentially choose one of the two options. He can actually either put a copy 1 and then take this string, compute the hash value of it, and he will get a hash ID. And with this hash ID, essentially he will now float a query. He will send a query message to this particular hash ID. So this hash ID will be sent. This will be the destination. And then he will say this is the key which I am searching for. So it will actually go to the root node 1. This will terminate there. And the key value pair is stored there. And it will find, and key value pair will be sent back. Okay. So for sending back, so whichever is the source, either actually it can go via DHT or it can directly go to the endpoint address which is given in the packet. So there has to be a source address also. So there will be a source address, so which can be directly IP address port number, or this can be a node ID, either of the two. So if it is node ID, it will be sent as a response. The query response message will be going with key value, certificate and everything. So alternatively, it is an option to also choose. Node can decide, okay, I am not going to do this, I am going to choose a key copy 1, key copy 2, and then compute the hash of it. So in fact, different node, when they are searching for the same key, they can randomly pick up copy 1 and copy 2. So they will essentially be going to two different nodes, and the load will get distributed among them. So this will compute a different hash ID. Again, when the query is going to be propagated with this one, this query will now terminate at root 2, which will then respond back to the same key value pair. The same thing is being kept at both the places. Now I can use this to my advantage. Okay, if root 1 dies off, what is going to happen? So in that case, if a node makes a query with copy 1, it goes to root 1, the response comes, there is no key value pair with this key which is existing. It can then search for copy by actually adding copy 2, and it will go to root 2, and from there it will find out what is the key value pair. So we can actually now build up a mechanism that root 1, whichever is the root 1 node, this is supposed to do a republish of whatever is the key value with key. If it is actually storing copy 1, it is going to put the hash ID to which it is going to republish will be computed with key copy 2, and this guy will be doing a republish with a hash ID of key copy 1. So in this case, if this guy dies off, this guy will be making a publish. This will end up in going to a different node, which will be a new root node. Okay, so this will be root 1 prime, and this guy will again do republishing, which will come here. So if it dies off, this will go to new root node. So root nodes will always remain. So they are essentially now trying to do a root. These root nodes are monitoring each other, and they are trying to provide backup to each other. This way entries are never lost, they are actually maintained in the system. Now the question arises, when it will be possible that both pairs which are actually holding key value pairs, so one is the root 1 and one is root 2. For a certain key, these are the two root nodes. When it is possible that key value pair will actually be lost. Because so far what we have done is we were assuming that both the nodes will not be dying together. But there is a finite possibility that even if they are far apart, they may end up in turning off together. So there is a risk which is involved. So when both actually die off simultaneously, then key value pairs will be lost. So in this case, the one important thing is that for every key, so how many keys will be there for whom these both will be the same root nodes. So when they will die, probably 1 or 2 keys will only be lost, not more than that. Because you change the key, the root node pairs will keep on changing. So the all keys which are there with him are pairing with different root nodes. Only probably one or two will be there which is pairing with this guy. So if these both dies, only those particular key value pairs will be lost. And if the nodes will come back again and they have stored it on a disk, the key value pairs will resurface again. So that's a finite bleak chance of actually losing. So can we remove that chance also? So maybe one possible idea is that instead of using 1, 2, I can actually have k. So I can have k root. So I will maintain now the k copies for this. K copies will be maintained. So that's a replication factor. Okay, but how this will actually be done? And then of course, who is going to take the monitor each other? In this case, this guy was monitoring this person, this guy was monitoring this, and they were doing republishing. So we created a kind of a circular backup of each other. In this case, how this will be actually happening? We also need to change something in our publication when it is done. So every node, for example, I have root 1, I have root 2, I have root 3. So everybody should know that which particular copy number it is holding. So when I am only storing, these root nodes are only storing key value pairs, we also need to now store which particular copy is being stored here. So there is a copy number which need to be maintained. I also need to maintain how many number of copies are being maintained actually. Total number of copies also has to be there. So these two data also has to come in now in each table. So the way this actually can be a parameter for the system, but it's better to keep it programmable. So when the source is going to publish, that time we will say that how many total copies have to be maintained depending on the worth of the key value pair. If you want that it should never ever be lost, maybe you can maintain 3 or 4. But even with 3, 4, this is going to be extremely reliable, Chances it will be lost is going to be very, very small. And because there is a continuous replication, even if one node dies off, there is automatically a next copy gets created. So in this case, the way the values will be stored, we will be actually need to have now in the packet which you are going to send, key and value will be there as usual. We will also be having digital signatures, and digital signatures will still be only on this, and of course now the hash ID does not make sense here. So hash ID is not included inside this the way it was actually told in the beginning. So hash ID now will depend on which particular copy you are trying to access. So this digital signatures only has to be on this, and then of course there has to be certificate. We will even modify this certificate thing and we will convert it to user ID as I mentioned earlier. Okay, so now we are going to add a copy number, which particular copy, and of course another field, total number of copies which will be added. So this is what will be the total data structure which has to be communicated during publication. And when you are doing the query, you have to essentially now send it to the hash ID, which will depend on which copy number you are trying to access. You don't have to worry about copy number, total number of copies there. You are just take the key, compute whatever copy you want. So you want a key copy number I, so you will put this I, compute the hash, and you got your hash ID. Route your query to this. So you can actually change any value of I. Okay, so 1, 0, 1, 2, 3, you can keep on trying. And if this number is a parameter which is available, if this number is a fixed parameter, then of course you know that you cannot go arbitrarily very large. But you can start 0, 1, 2, 3, 4, 5 till you find it, and when you will get the response back, you will know total number of copies which are available with you. Okay. So yes, that is one of the issues, that how much range which I should choose. So normally we can actually, in our Brihaspati 4 design, we have kept it at a fixed parameter value. We have kept it at 5. So 5 is the replication factor. For when I am talking about a storage system, there we have kept it as 2. So there will be total 2 copies which will be maintained, and 1 copy which with the user itself, because he will be maintaining his file systems copy. So in case of he dies off, he can always get the copies from here. Okay, but we are using there, we are still discussing about the mechanism which have to be used in that system. So once this is there, Now the question is what kind of keys which can be existing. I have to also tell you that there will be, as I told earlier, I think in universal file system. So for example, a movie. So I cannot put a name or something. I probably will take the whole movie content or movie fragment which is there. I will compute the hash of the content itself. Okay. And this is what is going to be the key for the content. So I will then append copy 1, copy 2, this particular thing. This is alphanumeric string. And then based on, and doing the hash of that will give me the location where this content will be there, and it will be indexed based on this key, which is the hash of the content itself. That will be also the indexing parameter. Okay. So that could be one possibility. Key can also be a string, an alphanumeric string, which is being decided by you. For example, for a DFS system, we use it something like, it's a DFS, we also define an email ID. And in the virtual file system space, where the inode is. I will actually talk about this file system later on. This we have to come to. And third possibility is, we are now introducing, and I think this will make a lot of sense. I don't want to store this certificate again and again and again. It's better to use only user ID who has published it. But to verify the signature, I need the certificate of this guy. So in the base layer of your DHT, I can actually put now user ID to certificate mapping. That's also like a key value pair. Okay. And this certificate will be signed by itself. This user ID key pair, this will be signed by the private key of the user ID. So you can actually look at the public key here and then verify, yes, this is actually properly signed. Okay. So from here you will be able to get it. This is another kind of structure which will be present. I don't require a certificate again actually in this case. The value is also certificate, and another certificate does not make sense. In fact, you need not actually do it. Because certificate will contain the user ID, so you just search for user ID. You can actually keep this thing blank, there is no value, and then there is a kind of a hash, signed hash, that this particular entry has been created by this certificate. So you can actually put some dummy thing here, some random thing. So in fact, putting a certificate does make a sense to me. Certificate is also a digitally signed stuff. With user ID, I can directly get the certificate, and that can be used to verify the digital signatures here. Okay. So that's what will be done. Now, how the backup is going to happen? So I have now many copies. How these copies are going to do the backup of each other? So one possibility is that I will, the ith copy will always be publishing I plus first copy. So it's forming a ring. Okay, this guy now does I plus second copy. So since we have also have total count also has been put here, total count of copies. So the last guy will be now publishing back to the first copy, copy 1, which will again do like this. So they are actually all, even if some node is lost, it will now find out some other node, which in turn will then get connected to this. So this is a new root node, I plus first root node, which will be the existing. So a larger number of this actually can be used for extremely high reliability depending on your application requirement. In Brihaspati, we are actually going with only 2 as of now, but if you require, you can actually have higher also. Now we can further innovate. There is a possibility that one of the root nodes is a rogue node, and you publish, and this guy keeps a garbage entry, he is not publishing any further. So you can actually publish on both directions. So you can publish to I minus first also, every node can do I minus first and I plus 2 in the cyclic fashion. So even if one node is rogue, so from other side you will be able to publish the whole thing. Even if one node is rogue by chance, so when people will try to find it, they will not get the entry when the query is going to be sent terminating here. So normally a good idea for making a query here is make a query to at least 2 or 3 guys, and then use the majority logic to get the key value pair. Is depending on what's the value of that particular data which you are looking for. Now, so far key value pairs were not having expiry. So, but every key value pair also need to have an expiry. So this will be done when the publish will be done. So this is absolute expiry which is going to be maintained. So I am actually putting my certificate and everything. This will expire in 6 months. So in this case, I need to have an expiry entry which has to be made here. So when I am going to make the entry, that time I am going to put the expiry period, say it is 6 months. But then I also have to give another value which is going to be when the entry was created, creation date. So creation date and expiry period, based on that I can figure out when this entry has to be purged from the database. Now source has to actually put in this entry before this expiry happens. Okay, but this will be removed. Republishing is only done so that you go to always to the correct node. But what's the life of that data is decided by the source. Now there will be some sources which, for example, like a movie. So I am actually putting a movie, and the way it is done in our design is by computing the hash of the content and that hash ID. So you will do hash of the complete movie content, and this hash ID is the key for this. So far somebody has this hash ID, this will be accessible. The moment this hash ID is lost, if nobody is having this hash ID, this content cannot be retrieved actually. So I need to clean and purge all these extra, what we call orphan data structures. So one way to do is I will also now set up a flag here. So I will create the entry, I will set up a flag, and this flag is F. F means if F is 0, this is not final. Okay, and when F is 1, this is final. So when user ID and certificate kind of entries will be there, I will make F is equal to 1 and set up the expiry. So this expiry won't change. So from the creation date, after that much period, this entry will be removed. But if it is movie, I will set F is equal to 0. It is not final. And I will set up a say expiry of 5 years. So we have built a mechanism whereby the moment somebody accesses this particular content, this expiry is reset. This expiry is reset on every time the content is accessed. So this essentially gets a, if nobody is going to use it, nobody has accessed for last 5 years, then we can actually purge this entry. For this kind of perpetual content, this is a perpetual content, this is not final actually. So if something is in use, it will remain forever in the network, somebody will always be holding it. And so far this hash ID is there, with somebody, he will be able to access it. And if hash ID itself is lost, nobody is holding it, this will anyway will expire and will be purged from the network. So it will not be essentially creating a burden on the system. Okay. Now in case of expiry reset happening only in one of the root nodes. So they are root 1, root 2, root 3 and so on. So root n, for example, are there. The query actually came here and this is holding a universal file system. For example, the movie, the case which I am taking, and movies, the F field is F is equal to 0. Okay. So in that case, a reset will be happening here for the expiry, but the reset will not be happening for the entries here. So the rule is whenever a publication is going to be happening, so for example, it will publish to the root 2. So when root 2 will be receiving the entry, it will figure out that the expiry value for the entry which is coming to me, which is as a replacement because of the republish, is actually better. So in that case, the earlier entry will essentially be is also reset timer will be, expiry timer will be reset in that case, even for this. So this will, they have the expiry timer reset will happen, and during republish, wherever it goes, there also the expiry timer reset is going to be done. It will be made equal to this guy. This will go this to the last person and ultimately to this place. So within a time, within no time, even if one access is happening, all the copies will have the same expiry reset timer. So this is important so that the file, the consistency of the expiry timer has to be there across all copies of the key value pairs. So this is how we actually can create the resilience. Now there are other methods also which can be used. We will be looking into those methods in the next lecture.